Hello, NSGIC. I hope everyone's having or is going to be having a great mid-year conference. I really appreciate you taking your time out of your busy conference schedule to view this webinar and to learn about one of California's data sharing programs. Thank you, of course, to NSGIC for hosting us. We really do appreciate our long-term partnership with NSGIC. My name is Luke Winters, and I'm a Senior Solution Engineer here at OneSpatial. And today we're going to be sharing an adapted version of a webinar that we originally delivered for transportation GIS users. The program that you're about to see is called CaRS, or the California Road Sharing Program, which is headed up by Caltrans, and it has a lot of collaboration with local governments and the broader state government in California. One section of this webinar will be hosted by Aaron Ott from Caltrans. This was originally recorded as part of that first session, and we're including it here because it provides a great overview of the work and lessons learned, and you'll get to hear from one of the leaders who's really making this whole project happen. CaRS is really about, sharing the roads. Not the physical roads, of course, but the data. And making sure that data is useful for all users, whether that's the locals maintaining the roads, it's the state GIS office aggregating those into a next-generation 911 network, or in Caltrans' case, creating a complete end-to-end depiction in a linear referencing system. There's a lot to a project like this. Planning, buy-in, adoption, and on the technical side, the big challenge is conflation, and that's where OneSpatial comes in for this project. That's what I'll be talking about, and then we'll have Aaron talk about the overall project. As far as why is this useful to state GIOs, this is essentially a transportation project. But like I mentioned, there's a lot of collaboration, and as Aaron will touch on later, there's benefits for all levels of government from this data sharing. By encouraging this type of collaboration between emergency services teams and the DOT will end up with better data, and this directly ties back to how they're provided funding to support Vision Zero, which is essentially providing funding to invest in making roads safer. Safer roads lead to fewer 911 calls, which reduces the burden on those next-gen 911 call centers. And of course, this also enables the creation of a more complete and accurate statewide roads data set for all sorts of use cases. Getting into the agenda then, first I want to go ahead and start out with level setting about what is conflation before we get into a few of the challenges and our approach to conflation. I'll then hand it over to Aaron to talk about the project in general, about what is the project, why are they trying to do it, and how does it work. And then we'll have a brief demonstration. So to start out with that level set about conflation, and I know many of you probably have done conflation work or know what it is, but there's also some who probably have not, or might not have a firm understanding of what we're actually talking about. So I just want to level set with that. In general, geospatial conflation is all about finding features which, although their electronic depictions may differ, they represent the same real-world object or phenomena, and then combining them in some way. How could you end up with those different depictions? Well, the first is spatial precision, right? Let's take an example that you walk down a road with a GPS in each of your hands. Even with that, just due to the spatial precision, you'll end up with different results. So you're always going to have some level of differences between two data sets. Another potential reason is temporal changes. There may be a new vintage of data collected that accounts for a change in the construction of a road, for example. Another potential is the style of a collection or storage. For example, dual carriageways, roads that have a median. How are those stored? Are you going to have a center line in the middle between the roads? Are you going to have one on each side? Are you going to have overlapping lines going in each direction? None of those are necessarily incorrect. It's just that there are going to be differences between the ways that they're stored and analyzed. Another reason could be the use case of the data. Take vehicle crashes, for example. Police officer might take a GPS point or estimated point where the crash occurred, but then a DOT might want to count all of the crashes along a certain road. And a point near that center line isn't going to really be useful to them. So they may need it to be snapped to the point, they may need to have it be an event on the line. Or the case that we'll be exploring today, where locals need a segmented network for routing, but a DOT needs an end-to-end depiction on each route. So those are some of the ways that you might end up with multiple representations of features in a GIS. But what do we do with that? Through conflation, we work to find matches between the sources, and then in various ways make them more accurate or useful. On the bottom of the screen is a very simple example of how this might work. Let's say the target layer is in green. It's a newly collected road data, but you don't have the linear events on it. We work to find the best matches for those segmentation differences and conflate that information over to the target, keeping your attribution from the legacy data, but updating the geometries. That's obviously very simplified though. And there's a lot of challenges that come with conflation. I just want to touch on a couple of these. If you want to dive more deeply into challenges on conflation, we actually have an entire webinar about that as well, so we'll just highlight a couple examples. You often end up having differing formats, accuracy, and data quality between sources. All of these can make it more difficult to effectively compare the data. Typically, conflation, because of how many comparisons you have to make, ends up being a manual effort. This, of course, means that it's a slow and resource-intensive process, and it also makes it more subjective, because if you have two different people interpreting the data, they may interpret it slightly differently. You may have different data standards in each format as well that you have to adhere to while doing a conflation, and you may have to combine data of different formats, like point-to-line, segmented line to linear referenced, or boundary to line, and so on. So there's a bunch of issues that can happen when you're working with conflation that makes it hard. This is our general approach to conflation. We do a lot of conflation, especially in transportation. And we've really sort of standardized our approach to this general format. We do it pretty differently, where we automate all of these steps using our business rules engine, which allows us to do this more consistently and be able to add slight tweaks as necessary. So first, we standardize the data, so that way you can take in data from any schema or geometric representation and reuse a lot of our existing rules. Next, we validate the data. We find that issues like missing ID fields, inaccurate geometries, or especially multi-part features can cause issues during the conflation process, so we always validate to start. Then we implement our matching process. This will differ a little bit depending on the specific type of conflation, like that point-to-line I mentioned, or segmented to LRS, as well as the customer's parameters, like how far of a search tolerance do we want to use. After we find the matches between the sources, we apply them, meaning that we transfer the necessary data to the target. So that could mean creating new features, transferring attributes from one to the other, changing segmentation, creating events, what have you there. After we've applied those matches, we revalidate the results to make sure that the data is fit for the new purpose, and the process didn't introduce any new issues. So that's our general approach to conflation, and now I'd like to turn it over to Aaron to talk about how California is using this conflation in one integrate to integrate the local next-gen 911 data with the DOT LRS.
Yeah, thank you, Luke. So today I'm going to explain some of the concepts behind our California road sharing project, which we refer to as CaRS. What the benefits are for those who participate. I'm also going to talk about how it is fully collaborative vision, which has involved counties, state governments, and the federal government. I'll talk about how it is funded on other concepts of success from the states, other concepts of success from states of Arizona and Georgia. And we'll show how it is a sustainable process for continual data sharing across the state, besides the California. Next slide. So the CaRS project is part of a pooled fund study of the states named Applications of Enterprise GIS for Transportation, or AGIS. This study is sponsored by the Federal Highway Administration. There's currently 13 states who are heavily involved and 6 who are friends or minimally involved. This study allows many DOTs to collaborate and share best practices that have been successful, along with the lessons learned from processes that may not have been quite as successful. The overall goal is that all state DOTs develop data governance standards and spatial data modeling standards for our enterprise GIS applications and our FHWA reporting. Next slide. From the beginning, the CaRS project was seen as a collaborative effort between all levels of government. The federal government requires all state DOTs to report asset information on not only the highway systems, but also all of our local roads through a process called the Highway Performance Monitoring System, or HPMS. A requirement of HPMS is that it is collected using the all roads network of linear data, or the ARNOLD model, which here at Caltrans we simplify as simply the all roads network. Funding for road improvements and maintenance in each state is determined by the information that each state reports. This makes it critical for the data that we submit to be as accurate as possible. A huge challenge is that most of the local agencies do not have the funding or resources to keep the road network up to date for the state DOT. This is across the nation, not just in California. This leads to the DOT having out-of-date data on the local road information. This project is the method that Caltrans is using to solve this dilemma and to make sure that we have current, accurate, and quality road data throughout our state. Next slide. All projects start because of some sort of challenge that needs to be addressed. The CaRS project is no different. It was created to solve the need of Caltrans to create and maintain our all roads network in California. We have a very robust process in place to update and maintain the state highway system. But of course, we also own that process, so it's much easier. Whereas we are sorely lacking in processes to get good, accurate information on our local road network. As you can see here from the last reported numbers, we have many, many more local road centerline miles than we do of the state highway system centerline miles. And so this becomes quite the problem for us. Next slide. The last update to our all roads network was completed through a contract with a local university, and it was completed one county at a time throughout the state. Unfortunately, this was completed at the beginning of 2023, and we do not have a system in place to consistently complete these updates over time. The university performed the digitization method using NAPE imagery, which itself was a little bit out of date. After the geometry was created, they did their best to check if it was a public or private road. This is important because we're only supposed to report public roads to the federal government. But one of the issues with using imagery is that you don't always catch the private roads. There's indicators that we use, but some of them get through. After verification that it is a public road, the geometry was edited into our all roads LRS layer. So one of the issues we have is that this process is both time and labor intensive. And as a result, we're behind in the updates on our all roads LRS here in California. Next slide. So this is quite the super graphic with a lot of information on it, but Caltrans is looking to minimize the impact of this effort that we're required on our local agencies. What we're going to do is we're going to use the next-gen 911 data that the counties in the state of California are already reporting up to Cal OES. When the county reports this next-gen 911 information to Cal OES, we're putting into place a system to then grab that data and convert it into the all roads LRS model. We're using the One Spatial software to do the conflation, the data quality checks, and the conversion from the next-gen 911 NEDA model into our California all roads LRS model, which we do follow the ARNOLD process from the federal government. This process does not add any additional burden on the counties to create or submit data to Caltrans to update our own road network. One of the challenges that we encounter is that we are using a more advanced model of an LRS. We do model out a dual carriageway, which for those of you that are not familiar with that term, is basically a divided highway. So here at California, and one of the issues with this is that the next-gen 911 NEDA model uses a simplified centerline model for roads. And you'll see in our demo how we deal with this. This issue did require us to experiment with buffer distances that gave the best results when we were initially working with Merced County in our initial pilot. After we convert the data into the all roads LRS model, we then use this data to report up to the federal government, and all of California is better off because of our improved updated data submittal. The state of California is actually so big that a bad data submittal from Caltrans actually skews a lot of the rest of the nation. So our vision is that we will then have the ability to provide, after we get through this process and we receive this data from the counties, we'll have the ability to provide all roads LRS information back to the counties for their own needs. And as we mature in this project, We actually aspire to be able to give the data back in both the ARNOLD data model and the NextGen 911 NETA model, to where the counties can then consume it back into their own data systems. Next slide. So this project is starting to get into the exciting phase, where we're starting to see the actual results. We've already completed phases 1 through 3, which were the planning, integration, and proof of concept that we did with the County of Merced. Many thanks to Jean from Merced County for being such a great partner. We are now engaging with 5 to 7 more counties to test out this process and ensure that it does indeed work. After we complete the pilot with these additional counties, we'll begin working with all 58 counties in the state of California. As I mentioned, we are trying to reduce the burden on the counties by not requiring any additional data submittal to the state. But at the same time, we are engaging with them throughout this process to see if there's any additional needs that we could potentially fulfill for those local government agencies that could be a byproduct of this project. Next slide. The goal and vision of this project is big. We look to create a statewide all roads network and a NextGen 911 network that is fully compliant with the California data standards. This in turn will allow all government agencies in California to benefit from better reporting to the federal government and help the federal government meet its own goal of the Transportation for the Nation initiative. All this will hopefully reduce everyone's effort and resources that are needed to maintain their own road networks, along with building greater collaboration and coordination of data sharing between all California agencies. Next slide. One of the great things about being part of this AGIS pooled funds study is that we get to learn best practices about what worked and what did not from each other. This project is not new. It was built upon efforts from both Arizona DOT to improve their ARNOLD data. It's also built upon Georgia DOT's effort to data share between local agencies. Being that California is indeed quite different from both Arizona and Georgia, we took both of their projects and created the CaRS project and put into it the best of both efforts in a way that will actually fit for the state of California.
Thank you to Aaron, of course, for giving us that recap of the project. We will go back to Aaron at the very end to talk about some of the benefits of CaRS and where it stands right now. In the meantime, though, I would like to go ahead and give a bit of a demo of the system, the process, how this actually works under the hood. We're going to be talking about both the validation portions as well as the actual processing of the conflation. So we're going to go ahead and jump in here into ArcGIS Pro, and it should be noted that we are DID agnostic. I'm just using ArcGIS Pro for visualization purposes today, but we do use all sorts of GIS. I just want to go ahead and mention the data that we're going to be working with. We're basically just playing the part of a submitter for Merced County. Again, they were the first proof of concept for this project, and really the only data submission that I'm going to be putting in for now. So that's going to be their next generation 911 data center lines, which are the ones that you can see in black here. As you'll note, a few things in the network is that they're all segmented at intersections, or at least they should be segmented at all intersections. And that's because, of course, the routing, it's for routing and addressing, as Aaron mentioned earlier. And so when we go into the complete setup, we'll see the differences compared to the linear referencing system and the ARNOLD routes there. So I'm going to go ahead and log into One Data Gateway, which is our data submission portal. Right now I'm logged in as Merced County, and I have all of my assignments available. These are basically the different workflows that we have set up for this project. So the first 4 steps here are validation. And like I mentioned, we always validate data before we do conflation to minimize any issues as we go through the process. So we have our essential geometry checks, and this is what I'll be running for this example. Our essential network checks, which go a little beyond just geometry, looks for topology and things like that. But we can have any sort of linear network, those sorts of issues there. And third is basically our subset of our NINA Next Generation Now 1 validations. That's taken directly from our SAS solution for Next Generation Now 1. And basically looks at those attributes, making sure that they are correct and meet the standard. Then we also have some cross-feature validations as well. And the last tile you see here is the conflation step itself. We're going to go ahead into the second part of the demo today. All right, so to start out, I'm going to go ahead and check my essential geometry checks, and I'll start a new submission. Right now, it's going to ask me for a file geodatabase, and I'll just drag and drop that in here. When that uploads, I'll go ahead and continue. We of course can set these all up for all sorts of different data. It could be a shapefile or a geodatabase or an SDE, or feature services if necessary as well. When I continue, the first step in the process is typically schema mapping. In this, we don't need to do that since we're just looking at the geometries. It's just going to take whatever the source schema is. We'll see an example of the schema mapping on the next section. After I press continue, we'll see the actual steps that are being run in this session. First thing we're doing is we're opening the data, loading that into the system, and then we're going to start looking at the validations themselves. So things like checking to make sure that the features meet the OGC definitions of being valid in simple geometries. We're going to look for those multi-part geometries, the self-intersections, overlapping features, any digitization errors like spikes or kickbacks, duplicate vertices, and duplicate features. So when we go through all the steps there, basically show us the overall conformance levels for each of these, and we'll have some that have 100% conformance, some that are a bit lower, lower conformance levels here, and we can see that we have a few features that are failing these different checks. So we can see the overall level here. But then we also are copying out our results. So if I go to a next screen here after we finish our submission, we'll be able to download this markup schema here. And that is going to be something we can bring right into ArcGIS Pro and see where those actual issues are. That makes so that you can really pinpoint those issues and go ahead and find those problems and fix them. So before I ran this live, I did bring our markup points into our map here. So I'll just go ahead and turn those on. And basically anywhere you see one of these plus symbols, that's going to be one of those non-conforming features. And we'll just run through a couple examples of the sorts of issues that can be found with the essential geometry checks. So in this area, we had some duplicate features. If I select it here, we can go ahead and see the markup point and the rule that's being failed. And we can see that we do have those two duplicate road segments there. So that's why those are coming up as an issue. Next up, self-intersections and spikes. Here it should be noted that on this, if I grab this line, we'll see two markup points at this location, both the self-intersection and the spike. And that's going to actually put the point right on the location of the issue, not just somewhere along the line. So you can really pinpoint where that spike is. Looks like it was just digitized out of order in this case. If we grab our vertices, we can go ahead and drag around, and you can see what happened there, seeing that it's a spike and basically a kickback. Let me double back on itself. All right, next up is a kickback. The reason this kickback and not just a spike is that it basically doubles back on itself. And the definition of a kickback is basically the differences in the angles. So if you have a certain angle on both ends, it'll be referenced as a kickback as well as a spike. It's basically, similar digitization error in this location. All of these sort of things can cause issues with routes, if routes are out of order with the measure values and those sorts of things. So that's why we validate these beforehand. All right, so now that we have our data validated, we can move on to the actual conflation part, which is what we're going to be looking at next. So just to go into the data that we're going to be running in this one, again, we'll have that local roads, those next generation 911 routes in black again. And then if I will also turn on our ARNOLD routes or our state LRS, and those are going to be in orange. So just like we were talking about with the different use cases of how they might be stored differently, we're going to have those local roads are going to be segmented at the intersections. The others are going to be complete end to end. And those are some of the things that the conflation step will take into account in this process. If I go back into One Data Gateway here, I'm going to go to my assignments and I'll go to the conflation tile. We'll start a new submission. This time it's asking for 2 data sets though, and only one was required. In this case, I'll just go ahead and grab the one and upload it for the next generation 911. This is really how you'd have it set up in a more of a production environment, is that the county would only have to update their, upload their network. And then like Aaron mentioned, eventually it'll be through the OMS services, and then it will connect to the linear referencing system afterwards. So in this case, we do have a schema mapping step for the different counties, because they each may have their roads stored in different formats for things like attribute names. So those sorts of things can be compared to the state, how it expects it. So we can go ahead and check our target and source classes and any attributes and switch those around as necessary. Again, that's that standardization step. That way we can have one set of rules, and even if we have different types of data. In this case, since it's exactly set, I'll go ahead and continue here, and then we can get back into the conflation process. So in this case, the first thing we're doing is connecting to the linear referencing system. So that is stored somewhere else. You only had to upload that next generation 911 data there. We then have some pre-processing steps where we have one rule check in here as an example that's checking for those multi-part features. Like I mentioned before with the validations, multiparts are one of the toughest things to handle with conflation, because if you have it, you have parts of different roads in different locations. You won't be able to find matches for them because the segmentation will be so very different. So typically, and in this example, we go ahead and explode those multiparts and then recheck to make sure that we no longer have them before we continue with the process. It doesn't have to be stored that way on the county side or on the LRS side, but just for the processing itself, it's best if we do that as a pre-processing step. We then do a couple more examples here where we are building out the road name, basically concatenating a few different fields together to make comparison easier. And then we get into the actual comparisons and conflation steps. So with this, because the LRS is end-to-end depicted, typically we'll find the most matches by buffering out the LRS road system first. So we buffer that out by first at 10 feet, and then we find all the number of segments that are completely contained within that buffer and where the street names match. Those are going to be the best candidate matches. So we start with the best matches first and then grow out our tolerances from there. So we start out again with that 10-foot tolerance. If we don't find whatever we didn't find with that first one, we go and look for a 20-foot tolerance. And after that, we basically switch it. And there may be some cases where the LRS is completely contained with the next generation 911 segment and not the other way around. So we'll go do the same thing, starting again with that 911 segment, buffered out by 5 feet, see if we can find any roads that are completely contained and have matching street names. We then do that again at 10 and 20. So as you can see, there's a ton of different comparisons that are happening really in rapid succession to find all of these matches. We then go ahead and basically do a no street name comparison here. And what that means is that we're really using a fuzzy tolerance to see how similar the strings are. And then in the last case scenario, we go ahead and remove the attribute check altogether and just look at the geometries to find matches in that way. And that's really because we want to find as many matches between the segments that we can, but we want to find those best ones first. And so that we don't have those false positives. After that, we are going to do some post-processing steps to basically create our results events layer, to segment that out, to label them, to create the measure values, and everything else like that. And the last step, of course, is writing out that conflation results here. I should mention that this step here is really the middle piece in that conflation workflow. It's the matching step. So from there, we basically have those matches. We have the proposals, as we call them, and then we take a look in our in just a minute and see what our proposals are. The last step would be then to apply those and basically integrate them in with the LRS or with NextGen 911 system. So for now, I can go ahead and continue just like before. I'll be able to download my conflation delivery file right here. All right, so with that, we can bring that into our GIS, and I'll turn on our conflation results. Most of the areas that you'll see will come up with these purple lines. These are the ones where the geometry is the all-road network, but they're segmented where the differences of segmentation are found on the NextGen 911 set. And that's really the key, is that we're able to reconflate those and resegment those so that they're useful to both parties. And we can see basically where the road names are, what the measure values are here. I'll turn on the attribute pane here. So if we look at the larger example, we'll see that that most of the areas are that purple line. So we do have those segmented features, but we also have some that are being called out as adds or deletes. Basically, they're saying they're found in one data set, but not the other data set. So we'll look at a couple of examples of those here. In this area, we basically have all three different sets here. The green line is basically saying that these segments do not have a match in the LRS system. So we have an underlying 911 segment, and we don't have an underlying LRS segment here. This would be something that the state could then look to bring into their road network to make it more complete. Similarly, if we go down here to this next section, this blue line here is saying that the opposite is true. We have an all roads network road, but we don't have an underlying next generation 911 network road. That last example is basically what's called a gap. And this is just saying that at that location, we did have this, this all roads network piece here, but in the conflated values, we don't have a section on this last part because there wasn't an NG911 segment for that last little bit at that last location. So if I turn off our conflation results, we can see what that looks like here. In this section here, we have that black line, and the orange line here is continuous all the way through that part of the LRS road. So that does have a match. The bottom section here just doesn't. Basically, we're drawing that there's a gap in the network there. So again, from this point, we find where those features are missing in each of the data sets, and then we can do the application phase next, where we would apply those changes, where we could add back the new segments into the LRS and pass the new segments back to the counties from the other segment there. So then with that, I'm going to go ahead and pass it back to pre-recorded Aaron to give us a quick wrap up of the benefits of the CaRS project, where it stands now, and then we'll wrap up after that.
Yes, so to wrap up some of what we're talking about with the CaRS project, one of the things that is asked is, what are the benefits for everybody from this? So the way I see it is that this CaRS project that we're working on will revolutionize how we update our California All Roads LRS. This will allow us to update it consistently moving forward. And as we continue this project and get better data on the local road network, we will be able to update new geometry and also complete road name changes, which is one of the things we struggle with. And as all of our local jurisdictions build out more subdivisions, they build out more parts of their local communities, we'll start getting that information in a more timely manner so that we can be reporting it up to the federal government to be included in our our funding request. So as we get this better road data, everyone in California will benefit from the improved quality of our road network. And as we get this improved data, the local governments will be able to provide updates to the state highway system back to us, as we get this information, we'll be able to provide data from the local governments and also provide updates on our state highway system back to our local governments. This will empower all of California to more efficiently address some of these initiatives I have up on the screen. One of the big ones right now that we've actively been trying to address is our California Vision Zero, where we have a vision to have 0 fatalities on all California roads. And this includes bike and pedestrians. So while this is a large vision, it's a lofty goal that we are aspiring to. And the basis of it really is our road centerline network. Next slide. So how do we get the buy-in from everybody? So as I see it, this project is pretty much a win-win-win for everybody in California. A large part of our road funding is based on Caltrans's reporting up to the federal government. And through discussions with our local agencies, we're working in educating how that is important and why it is important to have good quality data to report up. This also lets them know that they directly benefit through potentially receiving additional funds for the maintenance and improvements of their own road systems. Outside of that direct benefit, we are building up a community and we're building up these relationships between the state and between our local government agencies. And we're opening up a data sharing pipeline that I hope can be leveraged in the future by both Caltrans, other state departments, and our local governments to keep that pipeline open both directions. And that way we can meet the needs for both our statewide projects and our local projects.
Thank you once again for listening today. I hope that this has been helpful and you've learned something about data collaboration and conflation. I hope you have a wonderful rest of your NSGIC conference. If you do have any questions, please feel free to reach out to me, or if you're at the conference, find Sheila and Kevin. I'd be happy to talk about CaRS or anything else that we've talked about in this webinar. And hope you have a wonderful conference.